Hello and welcome to another live broadcast from Slooh. You might have seen us yesterday, this morning, but we're on again because really the universe never sleeps. There's always something going on. And we're here because there was a magnificent X-class flare that happened just last evening that has sort of the world in a tizzy. There was a lot of interesting solar activity that happened. There's was a radio blackout that happened yesterday. All these things were going on. So we're here to get to the bottom of that. This is going to be accompanied by some live imagery of the sun from Canada to really get things rolling. We're going to see the sun as it is. We're going to see the sun as it's been. over the past 24 hours. And here to join me, of course, today is our very special Slooh astronomers. We have Bob Berman and Will Gator, who are going to be joining us for a really great broadcast that's going to get to the bottom of all these things. So, welcome, gentlemen, and thank you for joining me here today. Again, I've seen you just a few hours before for meteors, but hey, there's more stuff to talk about.
The universe doesn't sleep, Eric.
Yes,
It does not indeed. And please, our viewers, if you have questions, I'm sure there's a lot of questions going about what exactly is going on. Use the Slooh hashtag for this event. Hashtag sunny side up is what we're going to be looking at for this event. So do send us some questions along the way, and we'll be happy to look into them. But first off, I wanted to get to the bottom of a couple things with Will here. I wanted to know. I mean, there's so much to know. Just in general, what exactly has been going on here? What happened with this X-class flare, Will?
So we actually have to backtrack to yesterday evening, and just before actually we were about to go on air with our meteor show and our 3-hour meteor show, I see this notification in my Twitter feed. A solar scientist I follow, there's an X-class flare going off on the sun. We see these preliminary images from NASA's Solar Dynamics Observatory, and that's what you've got there on screen. That fantastic image there shows this flare going off. And X-class flares are something to get excited about in astronomy. These are the most powerful class of solar flares we know. And so we've only had one, I believe, earlier in the year. That was in March, and that was the first one of 2015. So this is really exciting to see. And as you can see, it's quite an extraordinary event, very impressive visually in these images.
It's so big, and there's all this wonderful imagery that has come out immediately from NASA and the Solar Dynamics Observatory, and we're very thankful to what they're providing here. But this one gives just an amazing comparison. Here's the Earth to scale with the flare itself, just to bring that to your screen, because yeah, the Earth is dwarfed by this event that really doesn't take up too much room on the sun, though it is pretty significant. And I also wanted to bring in our live feed just now from Thunder Bay, Canada, where we're showing the sun as it is, comparing sort of this region that we see here on this image to what it sort of looks like now. And there it is,
Look at
coming
that.
in live.
Isn't that
We see,
fantastic? That is a live image of the active region that produced this flare. So those dark spots you can see are the active region. And actually, it looks like there's a little bright patch there. So who knows, over the course of this show, we might see another flare, because it hasn't just been this X-class flare that this particular region has unleashed. There have been smaller ones as well. So this is one of the things I love about solar astronomy, and particularly using solar telescopes like we have live from Thunder Bay here, is the sun at these wavelengths is so dynamic, and anything can really happen in a course of minutes.
yeah, I'm just amazed by this brightening region right here. Like, look at that. As it keeps on going there, and you see this sort of haze that's going over the imagery. That's clouds over in Thunder Bay. So you're gonna see just how very live these images are, because we're seeing clouds themselves cover across occasionally. But yeah, this is our feed partner right here, and I see these three different dots. It's really so dynamic and fascinating. But you were also talking about, yeah, that this isn't the only flare here, and there was some issues over on the Pacific just yesterday with some issues with people that maybe have ham radios might have noticed. What was sort of going on there?
Yeah, so when these flares go off, basically what you're seeing, of course, with our solar telescopes and our orbiting satellites like SDO, you're seeing that tremendous release of energy radiation. So one of the big signals of these solar flares is a lot of X-ray radiation, and you also get an emission of radio waves, and that's what causes the radio blackouts on the Earth. You get this sort of they call it a sort of radiation storm from these particular events. So these sort of events, it really does remind us that we're connected to the sun in this sense, and that if this particular region moves into view, if it as it turns around and maybe flares again, if we have another big flare, it could release material in our direction potentially. If we have the right conditions, that's the sort of thing that can create, for example, auroral displays on the Earth. So this is why this studying regions and studying this sort of solar activity is very important, very interesting.
So yeah, we have this huge X-ray flare and that can like remove material from the sun. Was that a flare that will cause anything to hit Earth?
No, so basically this particular flare, you had something associated with it, which is called a coronal mass ejection. Now, you don't always get coronal mass ejections with solar flares. Sometimes you do, sometimes you don't. But this particular one did release one. I think, do you have that SDO video? You were showing me earlier a fantastic
Oh yeah.
video of the eruption. Can you play that one? Because you can see it very clearly in that video. The flare occurs. And then you get this associated sort of ejection of material, and that's part of. So there's the active region, that bright spot. There it is, and you see that sort of flame-like protrusion that sort of erupts outwards. Well, there's a lot of mass essentially. There's a lot of material being thrown out in these coronal mass ejections. We're talking of the region of billions of tons of plasma, and that travels out into the solar system, and that can actually interact with the Earth, or interact with the other planets, even the satellites that we have in the inner solar system and going around the solar system. So these sort of things, they're not always, they don't always occur with solar flares, but occasionally you do get them associated with particularly strong flares like this one. And as I say, they can come towards the Earth, and potentially they can cause, sometimes if the conditions are right, aurora display. So yeah, this one not in our direction, unfortunately, depending how you look at it.
Uh, but there was some significant activity that was happening, even though they weren't necessarily auroral displays. Is that we have this? If for those of you who maybe watched our meteor shower broadcast just yesterday, we were having a radio audio feed of the meteors, and this is from our same feed partner there, courtesy of Stan Nelson. He also looks at sort of solar activity, and this amazing sort of yellow and red dip through the middle of the sea of blue. That's signifying the flare that we see, and the vertical bar there is frequency. So it passes through a lot of different frequency ranges, and it's just a really severe activity in the radio range. So people are seeing it in different wavelengths. We were seeing it up there as well, and it's just it's so amazing to see it all across the board here. We have just an image here of it across a bunch of different wavelengths. But yeah, yeah, absolutely incredible.
It's incredible the amount of energy that's being released in this. We're talking like millions of atom bombs and just going off at once in that few minute period and releasing a tremendous amount of energy. And that is why they're such an interesting phenomena to study, really.
Absolutely. And how often do we get to study them per se? How rare is this sort of occasion to get an X, I believe it's 2.7 class flare?
Yeah, X 2.7, and then earlier in March we had I think it was a 2.1. So in terms of rarity, well, X class flares are the more rarer ones because of the much higher energy. But the sun, if it's got active regions on it, generally it's popping off all the time. It's sort of crackling away. There's little tiny activity. If you look at the GOES X-ray plot from the GOES satellite, you can see that the X-ray sort of emission, the flux from the sun sort of is up and down, and it's sort of like a jiggly line that goes up and down. So the sun is always sort of crackling with this energy, and this goes back to what I was saying earlier, the dynamic nature of the sun. We like to think that it's sort of a very constant force in our lives, but actually you look at it and it's this seething surface that you can see at these wavelengths. What we're seeing here is a region of the sun called the chromosphere, which is above what we would call the visible surface, which is known as the photosphere. And at these wavelengths, using these solar telescopes that we can see live here from Thunder Bay, you can see that material sort of being sort of corralled and sort of moving around in the magnetic field lines. I don't know whether you can see, Eric, but can you see those two little tiny sort of protrusions coming out from the edge of the sun?
Oh, right here, right?
Yeah, those are the ones. Those are called prominences, and again, these are massive sort of clouds of plasma that are suspended in these beautiful structures above the surface of the sun in the chromosphere. And these can sort of change over a matter of minutes. So, let's come back to those prominences at the end of the show, and, we might have seen a development.
And I'll be very interested to see what's going on here if we get some changes with this bright spot over here, because I wasn't seeing it when we were just starting the speed, so that's going to be interesting to look at. But yeah, you normally just think of the sun as just this yellow ball in the sky, but there's so much more to really uncover as you go through these different wavelengths. You look at it from different different perspectives, and you look at it through clouds, for example. this is a couple different clouds that are wanting to join in on the broadcast, getting a little bit of the star fever there. Uh, but yeah, there's so much really to uncover. We have lots of different images that are coming in from NASA as well. Here's, I think, a gorgeous one that we can look at. That's just from the Solar Dynamics Observatory that just is
It's
consistently
beautiful, isn't it?
observing.
We should probably talk about, the sort of mechanism that creates this sort of activity, because the sun, as you and I have both said, it seems like this constant force, this constant being, but actually the sun, is magnetically active. It's got a magnetic field which changes over time as even has a cycle of activity. So over 11 years, the sun's activity, sort of ebbs and flows, and we're just coming down really from a peak. But what happens is these magnetic fields, as they come out through the sun, they get twisted and contorted, and they start to build up magnetic energy. And this is what causes these magnetic regions. You have regions of particularly complex magnetic fields which begin to sort of store this magnetic energy, and it gets built up and built up, and eventually, through a very, very interesting and slightly enigmatic process called magnetic reconnection, the energy is suddenly released. And this is the driver behind these solar flares and these coronal mass ejections, this magnetic reconnection, which releases tremendous amounts of energies, like I said earlier, X-rays, radio, and you can see here, this is the result of this sort of magnetic activity on the sun.
And the sun is such a workhorse, such an influencer of all these different processes that really affect so fundamentally uh, Earth out so far in the solar system, as well as other planets. And I was wondering, like, how much do we know about these processes? Like, it seems like a lot of people were potentially surprised that this flare was happening on this day. It wasn't easy to predict. This is when this flare is going to happen. Like, how much do we have it down to a science? How much more do we have to go to really be able to fundamentally understand and predict these objects?
Well, I think it's fair to say we've made some tremendous advances in recent decades. I mean, we've had fantastic satellites like, well, the pictures you're showing are from the Solar Dynamics Observatory. That really has the sort of what we call the time cadence, the time between images that it's produced, has allowed us to see these processes going on, and also in incredible resolution as well. But there have been other missions like Hinode, and even there's a NASA mission called IRIS, which has really, really sort of probed some of these processes in real detail. So I think we're beginning to learn a lot more. But it's one of those things in astronomy. You often find these areas where you think, oh, we must know everything there is to know about that, and actually no, we do. We have a sort of top level understanding of it, but actually there are some processes underlying the incredible physics that is going on here that we still haven't completely sort of worked out, as it were.
Yeah, I mean, well, it's always great to have more places to explore. We certainly do on the sun, for one. But yeah, I guess one thing that I think might come as a concern to people who might be watching this is, do we have to worry about any sort of negative after effects of all this activity on the sun that we're seeing right now? I mean, sometimes that it can be a little worse than others, but do we really have to worry today?
Certainly not from this event. The radiation storm has passed with apparently no effect. I've heard no effect from any of the people who look after satellites, for example. They can sometimes be affected if the spot moves around and it comes towards us. In terms of the position, the Earth-facing side, what we call the geoaffective region. That is, if an eruption occurs when it's on that particular point in the sun, then potentially, any eruptions, say coronal mass ejections, could be sent our way. Then there are certain agencies, organizations who will be looking out at what will happen, but there's no reason to panic. I mean, it's more for people who are, for example, might be looking after communication satellites or, satellite networks, because these events can create charging on the circuit boards of these satellites, and potentially that can cause problems. In the past, there have been eruptions that have, in fact, knocked out, for example, power grids in Canada, most famously. But this is a very rare thing. It's not to say that we shouldn't be cautious and sort of want to learn more about these events, because it's it may be that in the future we get a very, very big one, and that could cause troubles. But on a day-to-day basis, we're lucky that the Earth's magnetic field shields us in quite a good way. But if there are any big eruptions, there are a lot of people who are already thinking about all the ways that we might sort of mitigate any effects of these particularly powerful eruptions.
And it's always great to hear that we're on top of things. We're looking out for the world here. I mean, if there were a particularly harsh one, would I have to worry about, say, my cell phone or my laptop or electronics and that sort of deal?
And sometimes if it was a particular, we're talking very hypothetically here, but
Hmm.
sometimes you might get your cell phone coverage, or your particularly like your GPS, that could
Mm.
be affected. The accuracy of your GPS under certain solar eruptions. But in the past, but if we go back to something like the Carrington flare, which was long before we had any of these electronics, if we had an extreme eruption like that, which was an extraordinary event, it was actually witnessed by an English astronomer, and he saw it with basically he was looking he had basically not like the fantastic space telescopes we have today. Essentially, he was looking at visible light, and he actually witnessed that solar flare himself, and it was an extraordinary event that sort of it's electrified. It's essentially the Earth's geomagnetic field, the magnetic field itself. We had auroras down almost to the equator. So some of these events can be very extreme, but they're very rare as the sort of the other side of that coin, as it were.
And so there you have it, folks. We have this incredible period of activity on the sun where we're seeing a lot of different things happen. The sun is providing us with an incredible light show. We're seeing all of this beautiful, beautiful imagery that's coming in from NASA, and seeing a lot of different things that the sun is capable of, but not really at a degree that's going to be extremely harmful to us here on Earth. And so it's an incredible opportunity to be a sort of a tourist in our solar system, to see some of the most exciting events that our little corner of the universe has to offer. And yeah, thank you, Will, for talking with me a little bit about what's been happening over these past 24 hours, because we've all been curious about what has precisely been going on. And so we still have a little bit more to talk about here, though. We're going to take a short break, but right when we come back, I'm going to be here with Bob Berman, and we're going to get a little bit more into the fundamentals of these flares, what they mean to us, why we can see some of them, why we can't exactly see certain parts. And that's coming up just in 30 seconds. So stay tuned. We'll be right back. Hi, everyone, and welcome back to Slooh's live broadcast, where we're talking about the interesting activity that has been happening on this super active sun over the past 24 hours. We got this interesting X-class flare. That's the strongest flare you can get on the sun, and it's the strongest flare we've had this year. So lots of drama, lots of activity, and we're here to talk about it live, to really get into the details about it. And so we had this great conversation with Will, sort of hashing out the past 24 hours. And here I am now with Bob, who is the author of The Sun's Heartbeat. So he has a lot of capability of talking about this solar object that we have in our solar system here. So welcome, Bob. Thank you for joining me today. And I think there's going to
Pleasure,
be a
Eric.
lot of interesting things to talk about.
Absolutely. And let's back up and think about what we're looking at here. When we see the ball of the sun and the stuff popping out of it in different wavelengths, as especially what's happening over the last 24 hours, let's really be clear. Because we haven't been since 1920, when Arthur Eddington first told us how the sun shines. We had suspicions. Will mentioned the Carrington event. That was 1859 when we first saw an amazing solar flare. Then in 1921, just 1 year after we figured out how the sun shines for the first time. We had another amazing event that threw material and radiation towards us, and telegraph lines were crackling with power, and people were knocked unconscious. Telegraph operators were knocked off their seats, and a fire started in the New York Central Railroad main office because of just the crackles and sparks and power that had come down from the sun. And then on March 13th, 1989, we had a quarter of Canada knocked into darkness because of solar energy that courses along the ground beneath the auroras and beneath the activity. So darn right it can affect us, but it all starts in a little ball in the center of the sun, only 1/300th of the sun's volume. We're talking about, picture in the middle of the sun a little ball, and that's where the fusion happens. That's where every second 96 billion hydrogen bombs are going off. 96 billion 1 megaton H bombs per second in the center of the sun. So that starts it off. Where we're seeing the outer part of the sun is just where it's released. That's just where the energy manages to escape. And if it looks sharp to us, that boundary, it's because it's only 200 miles thick, the photosphere, where all that nice light and infrared comes out. It looks sharp because it's a very thin layer that emits it. But even of more interest to us is something we only discovered a few years ago, thanks to this armada of spacecraft that we've got, STO and SOURCE and STEREO and TRACE and ACE. It's just, we've never had anything like that. And that is, there's a second sun within the sun. Not just that little fusion core, but the middle 70% of the sun rotates as if it were a solid rubber ball. And from that point outward, the sun rotates chaotically, with the equator taking a certain amount of time, about a month, and the poles taking 10 days more. And where those two boundaries meet, called the tachocline, that's where the magnetic field is generated. Not in the core the way it is with Earth's case, where our magnetism starts all the way on our nickel iron solid little core where it meets the liquid outer core. No, in the sun's case, it's almost to the edge. It's 70% of the way out. That's where its magnetic field is generated, and the magnetism, as Will said, is what produces all this spectacular effects that we're seeing: the X-rays, the flares, the prominences, the coronal mass ejections, which we only discovered in 1978. We didn't even know about them when the poor Apollo astronauts went to the moon. They were oblivious of the fact that they could have been killed by a massive CME, which actually just happened a month before one of the missions. So they got a little lucky there.
Well, there's so much going on with the sun. It's absolutely incredible to really talk about, because there's no end. We could go on forever. Really, it's great. And I just wanted to bring up real quick that our feed partners over in Thunder Bay, Canada, have just been not thundered out, but they've been rained out. So we're not getting any more from them. So if you are somebody who just popped into this broadcast very recently, head over to the first half and check that out for a little bit, because we have some great live imagery of the sun that was coming in in the first like 15 minutes or so before the clouds came and decided they wanted to take control of what we could see from the ground there. But that's there and that's available. But we also have still much more to talk about. A lot of interesting things. And I think I have a Twitter question here for you, Bob. That's it's about the aurora, where people are very curious about, the effects that this will have. If it's certainly not going to be incredible chaos, but what about what they could do for our visibilities, depending on the latitude? We have Jay who's asking, will this produce auroras further south than usual? Do we have an idea of whether that will be the case?
This one won't. Will mentioned that the storm has to be in the correct position. So I'll elaborate on what Will said. The correct position is when the object rotates around. Remember, it takes about, well, the sun actually rotates in about 25 days near the equator, but because we're going around it at the same time, from our perspective, it looks like it takes 28 days. So just about a month, the same period that the moon rotates. Isn't that funny? We have only two disks in our sky that look the same size, and they both spin in the same amount of time. They're the same size in their appearance, and they spin in the same amount of time. Okay, so here's this flare right on the edge, this second class flare. It's going to take 1 week for it to get to the center. And believe it or not, the center is not what's going to produce an aurora. We want it to rotate an extra 2 days going to the west of the center, to the right of the center. And then it's in the perfect position where it can follow the sun's own magnetic field lines. It's shaped a little like a lawn sprinkler. You know, that kind of curving spiral. If you have one of those rotating lawn sprinklers, the water comes out in an interesting curvy pattern. Well, that's what the sun's field looks like. It's called the Parker spiral. When a flare, or especially a CME, a coronal mass ejection, gets to that spot, 2 to 3 days sun rotation to the right of dead center, then it can throw material in our direction. But even then, that's not the end of the story, which is why aurora predictions are often wrong, because the blast is like a shotgun blast of pellets, broken bits of atoms, and this cloud of material, billions of tons it can be, tumbles as it moves, and it has its own magnetic field. So what will happen when it reaches Earth's magnetic field is anyone's guess, because it depends upon how it's aligned with its tumbling when it gets here. If its field is aligned opposite ours, with its own magnetism south where our field is north, then it can transfer its energy to our magnetic field, and then we'll get auroras. But if its field is aligned equal with ours, it can't, and the energy is just harmlessly channeled by our magnetosphere, flows behind the Earth and continues on, and we don't get auroras. And that's why these storms on the sun sometimes produce great auroras and sometimes they don't. And we really only know when the material is about 1 million miles sunward of us, where we've got actual satellites sitting at the place where our gravity and the sun's balances. And that actually samples the magnetic polarization at that point. And then we have only a few hours of notice. Then we know what's happening. I just got back from Alaska, leading a group to see the auroras from the last series of tremendous storms, and that was great. But you don't want to be in Alaska right now, because it's a little bit too close to the summer solstice, and it's twilight or daylight too much of the time. There's only a very brief period of darkness now, so I'm afraid to see a good aurora, you need more than just the right solar circumstances. You also need night, which is why all those people who take cruise ships to Alaska and then tell me afterward, well, I went there and I didn't see any aurora. And then I try not to be sarcastic, but I'll say, but you went there in July, didn't you? And was there any night at all? No. So that's why there's no aurora. But our questioner wondered whether the aurora can spread further south, and they do. We had that in 1989, and we had great auroras in the autumn of 2000, 2001 that went very far south. So we definitely get them when the storms are powerful enough.
Yes, indeed, and it just speaks toward how sort of precise the conditions have to be to get these great aurora. And I'm thinking back to the trip that you did just a few months back, Bob, where there were just some really glorious aurora from your view, and also from Paul Cox in Iceland. We have some great videos way back when. So yeah, Slooh members, take a look at those if you haven't seen them yet, because those aurora are really like once in a lifetime sort of deals. Like, when was the last time you saw aurora as beautiful as you last saw them, Bob?
Well, before this time that we went there and we captured them for Slooh, it was the year 2000. And we're there in Alaska bringing groups to see auroras every single year since then. And it's been that many years, since 2000 and now. Let's do the quick math. How many years is that? 15.
2000.
So that's how many years it's been. So it's unusual to have auroras that are that spectacular. The best ones are not just bright and not just vividly green. That's the most common color. A truly blood red aurora is a once in a lifetime experience. But you also want to see motion. There's always some leisurely motion, but rapid motion is more desirable, and we got that. We saw that. And so the stuff that's coming now, and especially on the far side of the sun, as the sun rotates, are sneaky spacecraft that are orbiting the sun, not just the SDO, the Solar Dynamics Observatory, but we've got a pair of spacecraft called Stereo that look at the sun and can see the far side. And we're told that coming up on the far side are some more solar storms. So even though the current solar sunspot cycle number 24, has theoretically reached its maximum already. Maybe it hasn't. The last maximum had a double peak, and we're starting to see a double peak in this one too. And it could be that we're now getting, and look at these different wavelengths that we're showing you, the sun, the same moment of the sun, but in different wavelengths of light. On the left, what the eye sees, and on the right, much shorter wavelengths, X-rays and other parts of the spectrum that we cannot see. And the sun's center, everything comes out as gamma rays and some X-rays. Invisible light, the sun's heart is as black as coal. It's pitch black in the center of the sun because it's so dense that you can't see far, and the energy is almost entirely in gamma rays with some X-rays. But as it leaks further and further out, what the sun actually puts out at its visible surface, its photosphere, is about a 50-50 blend of infrared, which we perceive as heat, and visible light. So when you see X-rays managing to emerge, that's powerful stuff. And that's what we're seeing now, these tremendous flares, evocative of the days of old. When,
But we are seeing these solar flares, but it's sort of like 4 out of 5 doctors see the solar flare. We don't quite see the solar flare on the far left image here in the visible spectrum, where it's not there. And so why is it that in certain wavelengths we're seeing this incredible burst of energy, and in others we aren't?
Well, our eyes were designed, and of course here at Slooh, we're not going to get into design by a creator, design by the intelligence of nature. What I just mean is that it's architecture. We don't get into philosophy or religion here. The architecture of our eye is such that we're sensitive to just those wavelengths that the sun puts out most strongly. And the sun puts out visible light, green, red, blue, primary colors of light. That's its main emission, along with infrared. We sense infrared, not because we can really sense it, but we feel the way it makes atoms jiggle. Infrared makes atoms move, and moving atoms are heat. So when it hits our skin, we feel it as warmth, and we say, oh, we will feel the warmth of the sun. What we're really feeling are speeded up atoms on our skin caused by infrared. So we do sense the infrared indirectly, and the rest of it is we sense the visible. But we can't sense gamma rays or X-rays because the sun usually doesn't put out a lot of X-rays and gamma rays. And what would be the sense of being able to perceive something that's not around us, whether we're looking for a hamburger or our socks or searching for, the hunter-gatherers, a bunny rabbit in the woods? It would be pointless to look for these by the light of X-rays. First of all, X-rays go through things. They don't even bounce off. I mean, gamma rays go through things. X-rays actually can be made to bounce, but they don't bounce off little soft furry things like bunny rabbits. So, and there's not a lot of X-rays hitting Earth. There's almost none. So it'd be pointless for our eyes to be sensitive to that. Our eyes are designed to see the visible wavelengths, and that's the left image there. And so we just don't see the other stuff. Fortunately, we have clever equipment above Earth's atmosphere that can perceive X-rays and even gamma rays, and that's what's bursting off from the part of the sun's limb that's rotating into view. The left side is where the sun's coming toward us, and that's where we see what's to come, what's going to be in the center a week hence.
And so we see this incredible activity in one wavelength, and then we really just see black spots in another. It's definitely something that is very different. But in ways, these wavelengths, like you were mentioning, it's so great that we can have these telescopes that are capable of looking in these different wavelengths, so we can see different parts of the sun, see different activities. Like, what would be a really great thing for maybe visible light? Do you think, in terms of looking in the sun?
Well, those black spots are actually brilliantly bright. If we could just take those black areas of sunspots and just put them out against the blackness of space, they'd be too bright to look at. They'd actually harm your eyesight. They're brilliantly bright. It's just that they're less bright than the rest of the sun. And so either our Slooh CCDs or our cameras or our eyes have adjust themselves to see the sun generally, and that compared to the rest of the sun, it looks black, but it's actually brilliantly light. And the reason it looks black is because this is an area where the local magnetism on the sun is up to 5,000 times stronger than the rest of the sun. The stronger magnetic area is squeezing, has a kind of squeezing effect, so that material from down below can't rise up quite as rapidly. And less fast moving material makes for a cooler temperature, and cooler temperature makes for the darker color. So that's why we get the darkness. But at the same token, the higher magnetic field means that this is a place where the plasma on the sun, plasma is just broken bits of atoms, a fancy word for the things that atoms are made of. So they're broken. So we have protons and electrons, the stuff that atoms are made of, but they're not combined as atoms, they're just fragments. And they are electrically charged, and only electrically charged particles will follow a magnetic field. So we've got magnetic field lines that are very strong between these sunspots. And the plasma of the sun will run along these spots and form those great loops of material that we see. So everything we see on the sun is from magnetism. And you wouldn't think that magnets, we put them on our refrigerators and stuff. What's the big deal? These are kids' toys here on Earth. They're compasses and stuff. It's just not very powerful. But on the sun, it's the magnetism that calls all the shots, that throws material toward us, that makes these all the visible phenomena that we see, and affects our lives so intimately. And that's what we're seeing on the left, the effect of magnetism.
Wow, it's the sun provides us examples of activities that are so commonplace, just magnets on the refrigerator, everyday things in such extreme scenarios when compared with what we're so used to, and it's amazing to be able to see this and experience this. And so we're so happy that you've joined us here today, Slooh audience, to really wonder and marvel at these amazing sort of feats of the sun. But oh man, and thank you again for bringing in your incredible questions here through the hashtag Sunny Side Up. We have a question that has been sort of a theme through a couple of our broadcasts that is absolutely perfect to bring Will back into the mix with. Will, I'm gonna bring you in right here, and I wanted to ask you for our Twitter user Josh. Can auroras be seen with noctilucent clouds? Would it be an amazing sight? Hashtag Sunny Side Up.
That's a good question, actually. I'm trying to think of if I've ever seen a picture of an aurora with a noctilucent cloud. I think I have. The thing is it kind of alludes to what Bob was saying about observing the aurora in Alaska during the summertime. Is that noctilucent clouds are really a phenomena of the sort of mid-latitudes. You see them more sort of in northern Europe, here in Scotland, particularly good. I mean, you see them certainly from here where I am in the southwest UK. I've seen noctilucent clouds, beautiful displays. The aurora, on the other hand, of course, you'll need that to go further south if you're going to see it from a location like where I am in the West Country here in the UK. But I've definitely seen pictures of the aurora with noctilucent clouds, so it's not impossible. Yeah, you can actually see them, but I think you have to have a kind of sweet spot of a location, not too far north, so you've got that sort of polar twilight where the sun never really disappears below the horizon enough for that darkness. But also at the right time of year, because noctilucent clouds, a little bit like aurora, they have their seasons. And so really it's got to be the summer months, which makes things a little bit tricky.
For those of you who may not necessarily be on the inside joke, is that Will brought up noctilucent clouds on a show a couple weeks back, and everybody went gaga over this. Nobody had heard of the noctilucent clouds. We don't know where Will had heard of the noctilucent clouds. I think maybe he discovered them in some dark cave with this dusty book.
Yeah,
but who knows? But
no. I've heard of them for 50 years. For me, it was frustrating because I've never seen them, and I look for the sky, and I love the circumzenithal arc, and I look at esoteric and rare diffraction and refraction and phenomena in the sky, and I've never positively identified a noctilucent cloud. So for me, it was just a tease. Hearing Will say, and he's still saying it. Oh, we see them a lot here in England. So apparently, you got to be further north, I think, or else I've just been a bad observer.
Oh, okay. So
No, I
Will
think
and Bob were in the same cave and they saw the same dusty book. But they saw that and we all started Googling here. Like I particularly, I was like, what in the world? It seems like such a fascinating topic. And so ever since he started introducing noctilucent clouds into the vocabulary of the Slooh shows, we always seem to get questions about noctilucent clouds these days because they're really,
brilliant.
people are finding them
Hello,
interesting.
people.
And so I think you've twisted our arm here, Will, and that we'll have to have a show on noctilucent clouds. We'll have to find them and give Bob a sight of noctilucent clouds one of these days. But yes, so for
Yeah.
those of you who didn't know, that was what the noctilucent clouds are all about here. I recommend you Google them because it'll be a fun adventure. But yeah, we've had a great time here today as well. The solar flare that is really powerful and magnificent, but is also not going to do us really direct, dangerous harm. So take your worries, put them to bed. You don't need to worry. You just need to enjoy the beauty of the universe as it stands here. And so yeah, you're safe, you're comfortable, you have beautiful views. What more can you ask for? And I'd like to ask you, Will and Bob, what's your sort of favorite thing maybe about solar flares, about the sun is as we're wrapping up this broadcast? What about you, Will? What are your thoughts on that?
I think they're a beautiful demonstration of the fact that our sun is this living star. You know, we've got this star that really, is changing all the time. It has this strange cycle of activity. You know, we don't really understand a lot of the key points of some of the very sort of finer points of the physics that's going on behind it. And it's always going to be one of those things that interests astronomers, professional astronomers. And, it is our nearest star if we're matter of fact about it. We look up on a night sky, clear, dark night, see all these twinkling stars and thinking they're so distant. But, let's not take for granted the fact that we have a star right on the doorstep and it's an absolutely amazing object.
Absolutely. And really, what can you add to that, Bob? What are your thoughts there?
I love what Will said about not taking it for granted. I mean, my goodness, in ancient times, there's a ball of fire moving across the sky every day. Who is anybody picking up on that? And there's this
Mm.
ball of fire moving across the sky. So even as we learn more about it, and we learn that a million Earths could fit inside if it were hollow, and we learn finally in 1920 why it shines and never goes out, and all the rest of it, it doesn't lose its magic. The more we learn, the more in awe we are, including in today's show here at Slooh.
Absolutely. There's never like there's one thing to really be gleaned from here. There's that we're always learning more about this really incredible, dynamic, enigmatic beast that we have in the sky. That's always there. Such a big influencer of so many things that happen in our solar system in our day-to-day lives. And so we're so glad you're interested in it. We're interested in it as well. And so if there's more things that are going to be happening in when it comes to the sun, we're going to be on the case. So look forward to more solar shows from us whenever the sun decides to peek out and be a bit active in the sky. And of course, we have our other shows coming up. We have a nice show that's coming tomorrow evening on the seasonal nebula in the clubhouse. So if you're a Slooh member, consider watching that. That'll be a lot of fun. And also, we're going to have a show on the Saturn opposition, where we're going to have two astronomers in opposition arguing out a certain topic about the universe, and we'll see who wins. And what will the prize be? Who knows? But yeah, tune in to find out all about that. And thank you again so much for joining us today. It's been such a fun adventure, and we'll be out and live whenever there's more to update you with. So stay tuned. This has been Eric, Bob, and Will for Slooh. We hope to see you again. It does
That's
not indeed. And please, our viewers, if you have questions, I'm sure there's a lot of questions going about what exactly is going on. Use the Slooh hashtag for this event. Hashtag sunny side up is what we're going to be looking at for this event. So do send us some questions along the way, and we'll be happy to look into them. But first off, I wanted to get to the bottom of a couple things with Will here. I wanted to know. I mean, there's so much to know. Just in general, what exactly has been going on here? What happened with this X-class flare, Will?
So we actually have to backtrack to yesterday evening, and just before actually we were about to go on air with our meteor show and our 3-hour meteor show, I see this notification in my Twitter feed. A solar scientist I follow, there's an X-class flare going off on the sun. We see these preliminary images from NASA's Solar Dynamics Observatory, and that's what you've got there on screen. That fantastic image there shows this flare going off. And X-class flares are something to get excited about in astronomy. These are the most powerful class of solar flares we know. And so we've only had one, I believe, earlier in the year. That was in March, and that was the first one of 2015. So this is really exciting to see. And as you can see, it's quite an extraordinary event, very impressive visually in these images.
It's so big, and there's all this wonderful imagery that has come out immediately from NASA and the Solar Dynamics Observatory, and we're very thankful for. Hello and welcome to another live broadcast from Slooh. You might have seen us yesterday, this morning, but we're on again because really the universe never sleeps. There's always something going on. And we're here because there was a magnificent X-class flare that happened just last evening that has sort of the world in a tizzy. There was a lot of interesting solar activity that happened. There's was a radio blackout that happened yesterday. All these things were going on. So we're here to get to the bottom of that. This is going to be accompanied by some live imagery of the sun from Canada to really get things rolling. We're going to see the sun as it is. We're going to see the sun as it's been over the past 24 hours. And here to join me, of course, today is our very special Slooh astronomers. We have Bob Berman and Will Gator, who are going to be joining us for a really great broadcast that's going to get to the bottom of all these things. So welcome, gentlemen, and thank you for joining me here today. Again, I've seen you just a few hours before for meteors, but hey, there's more stuff to talk about.
The universe doesn't sleep, Eric.
Yes.